Hello everyone. In this video, I'm going to demonstrate the complete y86 sequential processor by running ASUM program, array summation program, as we did in the previous video. And as you can see, we have all the stages: fetch unit, decode and write back stage, and execution unit, and data memory stage, and PC update. And then all the modules are connected correctly with some control modules here. And we can see all the programmer visible states, such as PC value over here, and 15 registers down here, and what else? We have a condition code over here, and actually status bits, but we don't, we just ignore this status. Yeah, I think that is good enough. And then here I have one note, and one thing to let you know. Because we have two memories, one in the instruction memory and the other is data memory. But we actually generate one memory file, and it includes both instruction and data. And again, since we configure the same way for both instruction and data, we can use one memory file for both instruction and data. And another thing is, since we are going to write data to the memory, so every time you start over executing your program, make sure that you load the memory file to the data memory again. So you don't have to reload your memory file to the instruction, because you are not going to write to the instruction memory, but you are going to write data to the data memory. So every time you run the program again and again, then reload your memory file to the data memory. Okay. I already loaded memory file to instruction and data memory, which is a memory file of this object file, ASUM object file. And we executed until the first instruction in the loop. And we stopped at here because we couldn't execute MR move instruction because we didn't have memory stage before. But now we have it. But we don't want to execute all the previous instructions because I'm lazy. So in our data, since we have an instruction count over here, as long as we know how many instructions we need to execute quickly, then we can quickly execute those instructions and then execute slowly from MR move instruction. So let's count number of instructions we need to execute. So this is the first instruction, and then second, 2, and then jump to main, 3, 4, 5, jump to sum, 6, 7, 8, 9, 10, and jump to test, 11, and jump to loop here. So this MR move instruction is 12th instruction. So then we can quickly run first 11 instruction and then stop and then slowly execute from this MR move instruction. Okay. So then I'll set this frequency with 128 and then enable auto tick, and then stop auto tick at 11 instruction count. Okay, let's start. 3, 5, 6, 7, 8, 9, 10, 11. Okay, I stopped at instruction count 11, and let's see the instruction uh, instruction sorry instruction address. It is 77. Okay, yeah. This actually the instruction count 11 indicates 12th instruction because it starts is in the first instruction count is 0. So we are at the we just we are finished cycle 7 here of this MR move queue instruction. Okay, then we can finish this instruction and then check its output. So what it does, what this instruction does, it read data at memory address RDI and then put it to R10. So what do we have in the memory address RDI? And what is the address, the value of RDI? So value of RDI is the base address of this array, which is yes. So the 1, 8. And then we read 8 bytes from this address, which is 0D000, D000, D many zeros. Okay. And then we expect, sorry, what was it? Okay, so we expect to load this value to R10, right? Okay, so then let's execute the later cycles, remaining cycles. This is 8, okay, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So as you can see in the register 10, we see many zeros, D000, D000. Since it is not same order in here, because we are using little endian to store the data. Okay, then we are done. And then what is the next instruction address which is 81, and then next instruction is 81. Okay, it is correct. Okay, the next instruction is simple add instruction R10 plus RAX, and then result will be stored in RAX. And what is the value of R10? R10 is okay, the value we just loaded from the memory, and then R0 is just 0. Okay, so first we just add 0 to the value of R10. So we will then our RAX will have the value of R10 after execution of this instruction. Okay, let's go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, we got the same value at RAX with R10. The next instruction address is 83. Okay, the next instruction is 83. Correct. The next instruction is again add instruction, but it increment RDI value by value of R8. So what is value of R8, which is 8? This is the size of one data in the memory. Okay, this is quad word. Okay, so then which means we update address of the data we need to fetch. Okay, then the next after this instruction execution, we expect to see RDI value with 18 plus 8, which is, I guess, 20. Yeah, let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. We got 20 in RDI. That is correct. And next instruction is 85. Next instruction is 85 over here. And then we decrement, so we execute a sub instruction, which is actually decrementing the count value. So we have a number of items to add up, which is in RSI, and it is 4 over here. Okay. So then after we execute sub instruction, then we will have 3 in RSI, because R9 is 1, and we subtract RSI by R9, which is 1. Okay, let's go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, we got RSI with 3, and next instruction is 87. Okay, all good. And then again we test, we jump if it is we jump if it's not equal to 0. So then we should know that the condition code. So condition code will be updated by this sub instruction. And then if the outcome of this operation is 0, then we don't jump. But if it is not, since it's not 0, so we jump to the loop. Let's run it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So nothing changed in the register value, but we see the next PC 77, which is the first instruction address in the loop. Yeah. Okay. So then we will iterate 3 times. Sorry, 3 times. Yes. Sorry. Yeah, 3 times more, and then we will jump. We will stop this program. Okay. Then how many? Let's just stop for every iteration and then check whether it jumps to the loop or it just return falls through. Okay. Then how many instructions we have to execute for one iteration? 1, 2, 3, 4. 4 instructions, and then the next instruction we will jump or not. Let's run 4 instructions. 2, 3, 4, 5, 6, 7, 8, 9, 10. And the 1 instruction. Okay. Second instruction. Third. Okay, I just executed 4 instructions. And then now we are at 87, which is, jump instruction. Okay. So then, since RSI value is 0, which is the outcome of previous sub instruction, so we expect to jump to loop. Okay. Let's execute 1 instruction. And the next instruction address is 77, okay, the beginning of the loop. Good. Let's take the next iteration by executing 4 more instructions. And let's go. Okay, first, second, third, fourth. Okay, we finished executing the one iteration, and then we got RSI value 1, which is the result of the last sub instruction again. And then we will take another loop. Maybe it is going to be the last iteration. So let's finish executing the jump instruction. Okay, and then we got next instruction address 77. Okay, and then next what's that? Let's execute the last iteration. Okay, let's go executing the 4 instructions. First, second, third, fourth. Okay, so we finished the maybe last iteration, and then we are at PC 87, the JNE instruction. And since our the RSI value is 0, then we expect to see not jump to the loop. And we can also see the last condition code, but I think it is already changed before. Okay, let's just execute last instruction. Okay, so, sorry, we will stop the one cycle before of this jump instruction to see changes of this cond value. Let's run it. Okay. Okay, this is the one cycle before the end of this instruction execution. And as you can see, we don't have a signal from the cond module, which means we are not going to take the val c, which stores the address of first instruction in the loop. Otherwise, we are going to take maybe val p because we want to fall through. Okay, let's take one more cycle and then see the result. Okay, so the next instruction after jump instruction is 90, which is next instruction and return instruction. Okay, good. And then we can move on, and then this instruction will jump to the return address. What was the function called last call site? It was sum, calling a sum function here. So then we will jump to this place, like return another return instruction at address 55. Okay, let's run it. Okay, so as you can see, we got 55 in the instruction address PC. And also you might notice that the RSP was updated because we popped one value from the stack. And then next instruction is again, return instruction. Then it will jump to the return address. What was the last the corresponding call instruction, which is call name. Then we will jump to the add halt instruction at 1-3. Let's take a look. Let's execute one more instruction. Okay. Then the next PC is 1-3, which is here, and halt instruction. Okay. Then we are done for executing this program, but let's run one more execution to see how this processor handles halt instruction. Okay. So we expect to not update next PC value because we want to stop at this instruction forever. This is the definition of halt instruction. So when we execute one more instruction, okay, we are still at 1-3. Let's run one more instruction. Okay, again we are here. So we are stuck here. Then we are the program. So it indicates program stop, execution terminated. Okay. So then finally we can check all the program or visible states, and then check whether it is same with the value of YIS program, the simulation. Okay. So let me run asum.yo, and then we got this output, like changes of programmer's visual state. Okay. So it stopped in 34 steps at PC 0x13. So since we are having two different simulations, the actual cycles or ticks or steps shouldn't be same, but the others like PC should be same. So it stopped at 0x13. Yes, our program also stopped at pro PC 13. And then, so program status is halt and with some condition code. But actually, we don't check its halt status as I mentioned in previous. But we should check condition code. It is 0 bits are 1 is 1, and S and O are 0. It is same. So the most significant bit is 0 flag, which is 1, and the other two are 0. It's correct. And how about registers? So here we have registers. So it shows the changes to registers. It has two values for one register. The first one is initial value, and then next value is changed value. So it was 0 and then changed to ABCD, ABCD, and ABCD. So in RAX, we have same value, ABCD, ABCD, and ABCD. And for RSP, so it has a 200. We have also 200. Good. For RDI, it has 38, 38. And for R8, 8, 8, R9, 1, 1, R10, 100, 100, and 100. R10, yeah, 100, 100, sorry, A00, A00, A00 is correct. And then changes to memory. So let me open memory editor. to read memory value of data memory. Okay, this is the memory editor window. So then in this window, we can see the values of a certain memory location. So let's move to 1F0. 1F0. 1F0 is around here. Okay. So we got the 5 value in the least significant bit, or actually 5 at 1F0. So we have 5 at 1F0. And then we have 1 3 in 1F8. Where is 1F8? This 1 byte is in 1F0, and then next byte is at 1F1, 1F2, 1F3, 4, 5, 6, 7, 8. Okay, we have 1 3 at 1F8. It is the same. Okay, then we checked and tested that the output of programmers updated programmer visual states from both Logisim and the YIS are identical. So this program execution was correct. Okay, this is the final demonstration of this y86 and 64 sequential processor implementation using Logisim. Thank you.